Hi everybody, happy Wednesday. Hopefully you guys enjoyed like the nice warm weather yesterday. That's why we have the beach background. You guys did a fantastic job with your lesson quiz online, Pearson, so thank you for that. Yesterday we learned about just exponential functions in general. Today we're going to dive a little bit deeper and we're going to talk about exponential growth and decay. So we'll learn the lesson today. You guys will practice through an assignment, and then on Monday you'll have another practice day for it. Just because it is so important for your class for next year and for your Algebra 2 class later down the road. I just want to make sure that we take some time and you really learn it to the best of your abilities. So lesson 7-7, getting ready for it. And also this is your last day of school this week because you don't have school tomorrow or Friday. So yay for you. That's good. All right. So just a few reminders. This is another critical lesson. This is something you probably want your notebook out for, and you're going to want to maybe take some pictures of the notes, especially like the different formats with the formulas. So pay close attention to the video. If you need me, message me, but here we go. All right, so your goals for today, you want to be able to identify exponential growth and decay and be able to look at a function and say, okay, this is exponential growth, this is exponential decay, and I'll teach you how to do that. And you're also going to look to evaluate exponential growth and decay equations with values given to you. So those are your objectives for today. Just a quick review from yesterday. We started by differentiating between linear and exponential functions. Linear functions we've kind of covered all year long. Yesterday we dove deeper into exponential. So if I'm looking at this table up here, okay, these are two different functions that we're looking at. Let me just grab my pen. I can see that my x values are all going up by 1, which is fine. That could still be linear or exponential. But then I see that my y values are adding 2.5 every time. Because we're just adding that consistent value, that's going to be linear. Okay, you could write an equation for this. It could be y equals 2.5x plus 10, because 10 is your initial value here. So I know that that would be linear. It's going up by a constant rate. It's going to form a straight line. Down here, I see that my x values are still having a common difference of 1, but notice that your y values are being multiplied by 6. So you got 1 times 6 gives you 6, times 6, times 6. Because we're multiplying by that constant ratio, that's going to be an exponential graph. Even if you plotted these coordinate points, you'd see, all right, you're starting at 0, 1, 1, 6, 2, 36, and by that x value of 4, you have a y value of 1,296. That's going to be a way exponential graph. Okay, so quick review from yesterday just to kind of engage ourselves. All right, so when we're talking about growth versus decay, this is really what we're talking about. Now, obviously, you can probably tell that a graph like this would be growing, whereas a graph like this has an exponential decay. It's getting smaller as your x values increase. But notice that the equations for exponential growth and decay are still in the same format that we learned yesterday. It's still in that y equals a times b to the x. So that's fine. We know that. We've learned that. We've kind of internalized. What's different now? This b value right here, okay, if it's an exponential growth equation, b will always be greater than 1. Okay, because we're growing. So b would always be greater than 1. Whereas if we have a decay equation, b will be less than 1. So that's going to be one of the ways that we kind of differentiate together. Like, all right, is this exponential equation a growth or decay? We can always look at the b value to tell us what that's going to be. So that's just kind of your intro. If you have your notebook out, our lesson for today is exponential growth and decay. So that's what we're going to be looking at. All right, so let's go ahead and jump right in. Let's start with exponential growth. Okay, we're starting with growth. Notice that this equation is the exact same. The key difference is here, and this is important. This is something you're going to want to write down because in your assignment, you're going to have to match up the different variables and what they represent. Our A value is the initial amount. That's our starting value. That's consistent whether it's exponential growth or exponential decay. So if you had like a starting population of 3,000, that would go in for your A value. The B right here is your growth factor. So if we're talking about exponential growth, B is your growth factor. It's always greater than 1. To find out what that B is going to be, it's 1 plus the percent change is a decimal. So let's say that it's growing at a 7% rate. Okay, hopefully that pops up on the screen sometime soon. Okay, there we go. So if our population's growing at a rate of 7% per year, let's say, our growth factor would be 1.07 because we do 1 plus, like kind of like 100% plus that initial 7% growth. If our population was growing 10% per year, okay, we know that that'd be 10% growth right there. Our growth factor would be 1.1, okay, because we take 1 and we add that percent growth, it would be 1.1 or 1.10. So this is key for exponential growth. Our A in our equation represents our initial value, our initial amount. Our B is our growth factor. B is always greater than 1 if it's exponential growth because we take 1 plus that percent growth expressed as a decimal. You could also see it written as f of x equals a times b to the x. That's the same thing, and we've seen that before. Okay, here's just another way to kind of look at it. This is from your book. So if you need to look at this maybe with like the color differentiation, here's our exponential growth. We know that as x goes on, our y values increase. Notice this is the exact same, and our exponent we still have as x up there to show you that it's exponential. All right, so let's get into some applications here. Let's say that we're talking about economics, okay? Based on word problems like this, you're going to have to fill in each of these variables, and oftentimes you'll have to evaluate for y. So I'm going to teach you how to do that because sometimes it's not as obvious as you think. So it says, since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. So as soon as you see that you've got increased by 7%, you know that we're going to be dealing with exponential growth versus decay. In 2005, about $360 billion was spent at restaurants. And I know that Scott and I played a huge factor in that because we always eat out. If the trend continues, about how much money will be spent at restaurants in 2015? Okay, in 2015. So if I was looking at this right here, I know that I need to fill in my values for y, a, b, and x. Hopefully you kind of see, like, your y value is going to be the amount of money that was spent at restaurants in 2015 because that's what we're trying to solve for. Okay, so that's going to be the money that we solve for together. Remember that A is your initial value. So in 2005, that's the first year we're looking at, and it's 360 billion. Now we're just going to use 360. We don't need to use all those zeros. We'll just know that our answer is in terms of billions of dollars. So our initial amount is 360 billion. That will go in for A. B is your growth factor. Okay, because it increased by about 7% each year, we know that we can express 7% as 0.07, and then we add that to 1 for our growth factor. And this is kind of how I show you here. So what's going to go in for B is 1.07 here. Okay, and then X, this is your exponent that we have to fill in. That's the number of years since 2005. So if I started in 2005 and I'm looking at 2015, I know that there have been 10 years since 2005, so that's what I'm going to plug in there. And I believe the book also told you that, I just didn't crop it all in here. So now that we know what all of our variables represent, let's go ahead and plug that in. So here's what it looks like, you guys, and I kind of showed you for each part just to help you. This is something you might want to take a picture of because it'll help you with your assignment. So we're solving for y. We don't know what that is. We're looking at the amount of money that'll be spent in 2015. Our initial amount is 360 billion. Okay, we're not going to use all those zeros. We'll just know that our answer over here will be in terms of billions of dollars. Our growth factor, or our B value, is 1.07 because 1 plus that 7% growth, and then there have been 10 years since 2005. When you plug that in, make sure that number 1, you do your 1.07 to the 10th power first. Let's evaluate that exponent first, and then you can multiply by 360. And you get about $708 billion. So that was in 2015. Can you imagine in 2020 how much that is now? Sheesh. Okay, this is the next new part. We are talking about compound interest. Now, I know that together when we were in class, we looked at the simple interest equation. We even did a scavenger hunt for it. Compound interest is a little bit different, and the formula is a little bit more intensive with variables. This is a very real-world example of exponential growth, and compound interest is when the bank pays you interest on both the initial amount that you put in and the interest that's earned. Okay, so that means that the bank is paying you, like if you put in $100, the bank is going to pay you for that $100 you put in plus the interest that it's earning each year. So this is something, after I go through the whole next slide, you'll definitely want to snap a picture of it and probably write it down in your notebook for every single variable and what it represents. Again, not only will you have to identify those variables in your assignment, but you'll have to utilize them in an application problem. So here is your compound interest equation. All right, so here's what it looks like, and we're going to break down what each variable represents. A is the balance. That's like the total money that you're looking at. Okay, so after you go through this whole, I keep pointing to it like you can see it. After you go through this whole equation, this will be your final resulting balance. Our P is our principal amount, which is just the initial value that you put in. So if I put in $100, that's my principal. If my mom gave me $50 for an account, she never would, but if she gave me $50 to put in there, that would be my principal. R is the annual interest rate expressed as a decimal. So if it makes like 3% interest, that would be written as 0.03. Or if it made 11% interest, that would be written as 0.11. Okay, so remember that when you express R, your rate, that's always a percent and it's always expressed as a decimal. Okay, that's a common misconception for kids. When we're talking about N, that is the number of times that interest is compounded per year. N is the number of times interest is compounded per year. If it was compounded annually, that would just be 1 because it's compounded 1 time per year. If it was compounded quarterly, quarterly means 4, so N would be 4 because it's compounded 4 times per year. If it was compounded monthly, ask yourself how many months there are in a year, and there are 12, so N would be 12. And then T is just the number, like the time in years. So if we were looking at a problem that was talking about for 8 years, for 10 years, for 11 years, that would go in for T. So take a quick picture of this or make sure that you have this all written down, and then we're going to go through 2 problems together. All right. So here's my example. When Spike was born and joined this earth, my parents deposited $2,000 into an account for him to go to college. And of course, he's going to college. He's a smart dog. This account was compounded quarterly and earns 4.5% interest. What will the account balance be after 18 years? So right now, pause the video, take a second and see if you can plug in all those variables, and then we'll check with my slide in a few minutes. So $2,000 plugged in the account, compounded quarterly, 4.5% interest, 18 years. See if you can plug it in. All right, so here we are. Hopefully that yours matches mine. I also highlighted this so that it can kind of help you like show where the variables are allocated within the equation. Here we are. Okay, so it says $2,000. That's our principal amount. That's going in for P. Compounded quarterly means 4 times, so that is N because that's the number of times per year. Notice, look at the green highlight. Not only does that appear here for N in my denominator, but N also appears as part of my exponent, so that you got the 4 and you've got the 4. 4.5% interest, if you express that as a decimal, it's 0.045. Okay, if you had just 0.45, that'd be 45%. That would be insane. So it's 0.045. And then it says 18 years, that goes in for T, and that's right here. So here's how you can see it all plugged in. This might be another good thing that you want to take a picture of, just to make sure that you've kind of got it. So if I go through and simplify, here's my recommendation to you. Simplify everything inside of your parentheses first. So do 0.045 divided by 4, and then add that to 1. Notice that I also took 4 times 18, which gave me an exponent of 72. That exponent of 72 is only applied to your quantity inside of the parentheses. So clear out your calculator, take this value to the power of 72, and then you can multiply it by 2,000, okay? And then it would be about $4,475.53. So after 18 years, okay, my principal amount of $2,000 is now up to over $4,000 because it was compounded quarterly at a rate of 4.5% interest. Okay, if you were to get a number that was smaller than your principal amount, that's no good, and you should probably recalculate. Okay, let's just take a look at one more quick example. We're not going to go through it. I'm just going to show you how to quickly plug in your variables, and then you can solve on your own. So it says $5,000 was initially deposited. That is going to be my P value. That's your principal amount. If it's compounded annually, annually means one time per year. So number of times, it's going to be 1, and it's going to be a 1 here. If the interest rate is 5.6%, I know that I'm going to have to express that as a decimal for my rate, okay? And that'd be 0.05, wow, 6. Let's pretend that that actually looks nice. And then if 8 years go by, I know that that's going to be going in for t, so I would do multiply 1 times 8, and then my exponent would just be 8. Okay, and then you can just go in and simplify. So on your assignment, not only will you have to identify what each variable represents, but you also have to solve a few problems to find that compound interest. Okay, that was all for exponential growth. Now we're going to look at what exponential decay looks like. Okay, it's obviously kind of like the opposite. So if we're talking about exponential decay, notice this format of equation, y equals a times b to the x power, is nothing different than an exponential function general format. That's the same. A is still our initial amount. However, b is now our decay factor, and it will be less than 1. B is our decay factor because it's exponential decay, and it will be less than 1. For you to find what b is, you just take 1, which is kind of like 100%, and subtract the percent change. So let's say that there was an 8% decay rate, okay, or there was an 8% decrease. B would actually be 0.92 because 1 minus 0.08 equals 0.92. And you know that this would be exponential decay because 0.92 is less than 1. Okay, just to give you another example, let's say that my business had an 11% decrease in revenue. Okay, a decrease in revenue over the course of the year. That means that my decay factor would be 0.89 because 1 minus 0.11 would be 0.89. Okay. Again, this is just kind of what your book looks like, just to kind of show you and outline the variables again. You can see that this is a decay because as your x values decrease, your y values exponentially decrease. They go so quick. If I gave you an equation and I wanted you to plug it in, sorry, hold on. Computer's lagging. Okay, so here would be a problem for you to plug in. Okay, I'm going to give you a second to pause the video and read. If you were trying to figure out, because remember, this y equals a times b to the x stays the same whether it's exponential growth or exponential decay. If you're trying to figure out, like, is it going to be a growth factor or decay factor, aka is it going to be exponential growth or decay, look for clues in the word problem. It says the pressure decreases about 11.5%. That decrease right there tells you it's going to be decay. So you know that b is going to have to be less than 1. So if we were going to plug in our variables here so that we can evaluate and ask ourselves what is the approximate pressure at an altitude of 3,000 meters, we know that y is going to be whatever that pressure is. That's what we're solving for. Remember that a is our initial amount. So our initial amount in this problem is about 101 kilopascals. And please don't judge me for how I said it, just leave me alone. Now, b is going to be our decay factor. To find out what our decay factor is, remember, you take 1 and then you subtract the rate that it gives you. So 1 minus 0.115 would give us a, sorry, this should be decay factor. Sorry about that. So it would be about 0.885. That tells you right away that it's a decay, it's decreasing. And then x right here for our exponent will be the altitude in thousands of meters. So just so that you can see what to plug in there, okay? So just to kind of recap for you, exponential growth and exponential decay still use the same format of equation. A is always your initial amount. B is going to be your growth or your decay factor. If it's growth, b B will be larger than 1. If it's decay, B will be less than 1. Okay? And that's pretty much it. Remember, on Monday, we're just going to have a practice assignment, again, just to make sure that we've got it and we have no questions and no misconceptions. So your Wednesday assignment is an exponential growth and decay Schoology check. It's for you in the e-learning folder. Take it twice for your highest score if you score less than 100%. Make sure you have a calculator handy. That's going to help you. Other than that, fantastic job this week, as always. You guys continue to amaze me. Don't forget that we are playing our live game with Miss Nikki's class at 1 o'clock, so please tune in because it'll be fun. All right, see you on Monday because you have no school tomorrow or Friday. Miss you so much. If you need me, I'm here. Message me. Just waiting for you to talk. See ya.